Is to provide guidelines and recommendation for modeling fluid flow and species inside a biopharmaceutical chromatography column. This tutorial starts with the mesh geometry. As you can see, we have 4 inlets on top, and we have 4 outlets on the bottom. So let's get started. The first thing we want to do is go under General and set up the problem as transients. This is a transient simulation. We need to turn on the gravitational forces here, which is in the -y direction, so it's -9.81. And we take the default for the solver, so it's a pressure base, and then the velocity formulation is absolute. We will walk down the outline view to help us solve the problem and set up the problem. So the first thing we want to do is pick the right physics. So in this case, we are picking viscous. So this is basically the standard 2 equation K omega. We'll take the default values here. And next, we need to turn on the species transport. So we click on this and we turn on the species transport. Make sure that the diffusion and energy source is turned on. And then we leave the mixture basically as what the software has at this point, and we define it later. Next thing that we need to do is, after setting up the physics, is to set up the materials. In this case, if we go under fluids, we have what's called water liquid, and then I have what's called tracer, which is actually the water liquid, but we just renamed it. So the way you do this, you click on edit, and then you click on change, create, and then you would put the name of the basically species that you have. In this case, is a tracer. And we copy this over, and then basically it appears here as the fluid that we want to basically add. The next thing we want to do is define what's in the mixture. So in the tracer, if we click on mixture 1 and double click on this, it would take us to the tracer mixer. And these are basically the heat capacity and molecular weight. And we basically take the default. We also need to define what are the different basically fluids inside each one of the zones. So if we double click, and I want to do that just once so you can see, we have the mixture, and then we have there's no rotation here, so basically it's the mixture. And we can edit this, and we can see that it's essentially density is basically incompressible gas law, heat capacity is based on mixing law, and thermal conductivity is constant at 0.0454. Viscosity is 1.72. So this is for the mixture. So if we click on edit here, we see that we have the tracer here. So that's essentially the species that we have. The next thing we need to do is basically apply this for all the fluids, with the exception of one of the zones, which is called the porous zone. This is where we define the porous media. So if we click on this, and we have to check off the porous media, because this is basically the column that we're defining. And by clicking on porous zone, it will take you to another window where you will define the viscous resistance. So this is basically how much resistance it has, and it's equivalent to permeability of the material. And so that basically takes care of the fluid definition inside the chamber. And now what we need to do is define the boundary condition. So we have 4 inlets. They're identical. You have to double click on the inlet. In this case, we have under momentum, we define the velocity, and it's 0.25 meters per second velocity. Thermal, we just take the default, so it's at 300 Kelvin. And under species, this is where we define it, which is basically it's a file that we read, and it would allow you to actually input this as the value. And so we basically repeat this for all the 4 inlets, and then we move to the outlet, and outlets are identical as well. And so what you do is you, under momentum, you basically take the atmospheric pressure, which is 0 in this case, and then thermal, basically, we take the defaults. And so same here. So the tracer in this case is 0. So we're assuming that nothing goes back into the system. So that takes care of the boundary conditions. And next thing we want to do is go under methods for solution. And the most important thing is that the pressure is presto. And then everything, all the basically momentum and turbulence, tracer, which is the species, and the energy, they're all 2nd order upwind. And we want to basically click on the advanced options here, which is port phase gradient correction, and then the high order term relaxation. Double click on this, and then you get also click on the flow variables only, and set the relaxation to 0.75. This helps basically the solver to be able to solve as it goes through the iterations. Finally, what we're going to do is essentially initialize it. So my recommendation is use the hybrid initialization. So click on hybrid initialization, and then click on initialize. Once it initializes, the next thing you do is you basically set up the run. So the run calculations, because this is a transient simulation, we have to define the total number of steps and also the number of iterations per each one of the time steps, as well as the time step itself. So in this case, we're looking at 0.05 as our time step. The total number of times that I have is about 100, and the number of iterations. So what it does is that at every time step, it will go through 20 iterations. And once it's basically moves to the next time step and next time step until it finishes. And so what we want to do is basically in terms of output, we can look at solutions, we can define, so we go to edit. I have basically a report here, but it's really easy. So let me show you how to set that up. So we go edit, new. In this case, we want to look at what is exiting out of the outlets. So we have 4 outlets. So we want to look at basically mass weighted average here. And then we would select all 4 outlets. We need to make sure that we're selecting the right variable. In this case, it's species, and it's the mass fraction of the tracer. So since I already have this defined, I'm just going to cancel out of this. But that's essentially how you can actually monitor the concentration at the exits. So essentially what happens at the end is that we would run this simulation over the number of time steps that we had, and this is basically what we would get at the end. This is a series of concentration at different planes. As you can see, the tracer comes in, the chamber is empty in this case. The chamber is just the column basically, and it has some porous material in there. And so as it comes into the column, it starts dispersing and it starts expanding, and eventually it leaves the entire basically column. So you could actually look at the mass weighted average of the tracer as a function of time. I hope you found this tutorial useful. Looking forward to the next tutorial. Thank you. Bye.